This is lecture 13, example 2. What we're getting to is kind of the low-level implementation of these instructions. In particular, we are looking at the timing, fetch and execute timing of specific instructions. So this is going to be a big example when we're actually looking at actual timing diagram. Before last example, we just kind of looked at how the signals were being sent out, etc., etc. So this should solidify some of the stuff we talked about in the last example. So let's look at this thing. So what we have here is certain instructions that we are going to implement. And so these are the instructions. Hopefully you can see those. It's actually bigger on the next slide. And so let's go ahead and look at this. So these are some of the control signals. I divided them up between the decoder and the FSM signals. So these are the control signals coming out of the FSM. These are the control signals coming out of the decoder. And so let's go ahead and do this. It's very, very, very important problem. I don't know how else to say it. If you understand this, you understand. You're doing good. So please put the effort into understanding this. Okay, hopefully you can see this. So I'm going to there's a million ways to do these problems. I'm going to go ahead and start at looking at these instructions, and I see that I don't see any load instructions. So they're all going to break on these boundaries, and these are going to be, I'll just call it fetch, execute, fetch, execute, fetch, execute, fetch, execute, fetch, execute. Okay, and so I'm going to look at these instructions, and I have to pick up the spec here because I want to put the opcode on there. Okay, the opcode is actually the 7-bit rightmost 7 bits of every instruction. I don't have this stuff memorized, and so we will hunt down these opcodes. So this is an XOR. Looking at my sheet here, XOR has an opcode of 011. And read it. 0110011. Okay, so an OR I think is going to be the same. We're looking at OR because it's the same type of instruction. So 0110011. Once again, this is coming off. These are the 7 rightmost bits in the instruction word. I'm pulling these off the cheat sheet for the individual instructions. So SB it's an S-type instruction, so I'm pulling this off the spec. 0100011. SW is the same. 0101 00011. Okay, we'll get rid of this. 010011. Looks good. Or does it? That's right. Okay, the NDI, I know they're gonna be the same. They're 2 immediate type instructions. So I'm gonna pull this off the spec 2, 0010010. Okay, and that looks good. So I mean, a bunch of 1s and 0s. I don't know how instructive that was, but I did it anyway. Okay, and so here we are. We need to fill this thing in. So what I always think the easiest thing to do for this is the PC write. Okay, so the PC write, essentially it's going to load a new value into the program counter. We want that new value into the program counter there after every execute cycle. So as part of the execute cycle, this turns on. It actually makes something happen at the end of the execute cycle, which you'll see next. And so this is something that doesn't change. So I probably put too far of a delay on this thing, but essentially what these little delay here is saying that when it gets into execute state, part of the execute state is to assert the PC write. So I just put a little tiny delay in that thing. And so we are not going to see the offset. Okay, well, we're not going to see the offset. The other important thing in here is the associated signal is this memory write signal. So when I get into the fetch state, I have to assert the memory write signal. And so our memory write signal this is for program memory, is always going to be the same also, because it's essentially read enable for the program memory. And so that's not going to change either. These are solid things. So once again, I'm always going to be loading a new address into the program counter. This is the PC right here. I'm always going to be reading that new value from the program counter. The memory is synchronous, so essentially by turning this read enable on at this point, it makes the data available from the instruction available at the beginning of the execute cycle. Okay, well, that looks good. And so it doesn't really matter what we're doing here. So memory, this is a read from memory, which I'm not reading from memory ever for this problem. These are store instructions that's storing to memory, but I'm not reading memory. And so this entire problem, I can turn that off. Okay, so we're looking good here. So what else do we got? What we have is a reg write. So some of these instructions are writing registers and some of them are writing memory. And so what is really nice about this is this XOR instruction. It's reading two values and then storing the value in X5, which means that as part of this instruction, it asserts the reg write. Okay, so it turns off for the fetch cycle. And once again, this is going to be a similar type instruction here. It's an OR instruction. It's writing the result back to X5. I need to turn the reg write on, which is essentially the write enable for the register file. So we are missing the reg write or the reg select signal, but no big deal. Okay, so this was these two are store instructions, which means it's taking something from a register and storing it in memory. Certainly for these two instructions, we are not writing the memory. We're not writing the register, we're writing memory. And so we can actually leverage that in a second here. Okay, for these two instructions here, we are writing a register file again. So when these two instructions here, when we're not writing the register file, it turns out we are writing memory. These are two store instructions here. To make this actually the data from the register store in the memory, I assert the write enable. And so that is that. So for the memory, I'm not writing anything to memory when I'm writing to the register. So what's nice about these two lines here is that only one thing's being written. For these two instructions or these four instructions, I'm writing the reg file. For these two instructions, I'm actually writing memory. You can see that in the memory enables. In the memory write up there, so reg either writing to the reg file or the actual memory. So in this instruction here, we are doing this is essentially the FSM. These are the decoder functions. So we can oh, there it is. I didn't think we had this. We actually have it down here. Okay, so do we have this? We have a lot of cool signals down here, so not a big deal. Okay, so we can essentially go through this one by one here, and what you'll notice is all these things here are associated with the previous instruction. So I really don't know what they are, so I don't put them down. But what happens is once the output of that instruction becomes available because of this signal right here, the read enable has been asserted. All these values come out and we know what they are. And so they're only going to change every 2 clock cycles because that's when the next instruction happens. There's nothing to change it in between. Certainly these bits right here, well, let's put it in. This is an XOR. I'm going to read from my cheat sheet here, find out what an XOR is. It's on the top of my architecture diagram. XOR is 0, 1, 0, 0, 0, 1, 0, 0. That's for an XOR. Now the XOR bits are still here on the fetch and cycle. The next instruction, not a big deal, so this is how it's going to work. Okay, so the next instruction is an OR. So I'm reading my chart once again. 1, 1. There are my bits for the ALU function to do an OR. And here we are at the store instructions. So store instructions is essentially have to create an effective address from this offset and the base address. So we are actually using the ALU, and so we are choosing an add, and it's going to be the same thing for this one, 0, 0, 0, 0. Both these are has to use the ALU to create an add instruction. Okay, here we are at this point. We are at AND immediate. I got to refer to my cheat sheet to find out what the ALU function value is. And a 0, 0, 1, 1, 1. I absolutely do not have these memorized, or we already have that 0, 1, 1, 0, so we got another OR function there for this OR instruction. Okay, so I knew what these are doing because I knew what these instructions are. That's where these came from. So source A, let's look at source A. It's going to be for these two instructions here. Source A has to choose a register, so that's going to be 0 for these two. Source A is going to be 0 for these two here, because for the store instruction, it's still choosing a register value for the ALU source A, which is the 0 option. And so what do we got on this one? It's the same thing. So yeah, spacing out on it. Okay, so here we are at source B. Source B for these two instructions needs to be the register. Okay, so we'll put that in there. Now this is the lower part of the ALU. I need to choose the register to go in there. So this is 0, 0, and 0, 0. Looking good. And now for the store instructions. Store instructions are an S-type instruction. I know that from looking at the cheat sheets. So it needs to, one, we already got the register value loaded in there, but we need to choose an S-type for the source B option to feed into the ALU, which is 1, 0, and this is going to be the same thing. Once again, this comes from the fact that the store instructions is an S-type instruction. I knew that from looking at the cheat sheet. I look at the schematic. I see that an S-type is connected to the 1, 0 input on the source B mux. That's where these 1, 0s came from. And so this one, these are two immediate type instructions. And so these are immediate type operands. Immediate is associated with the 0, 1 input to that source B, mux in front of the lower part of the ALU. So once again, I knew these things right here because it was these are immediate type instructions. Immediate type instructions are I-types, which means it's going to use the I-type output coming from the immediate generator, and that's where that came from. So the PC source is going to be it's the value I'm going to load into the program counter. None of these are jump or branch instructions, so I can just fill these in real fast. It's questionable whether you have to fill these all in. I mean, it's not changing, but I like to make it look like it's changing, because you know, it might be changing. Okay, so this part, the register rate select, which is the mux in front of the register file. I need to see what's happening here. So these values, I'm taking the result from the ALU and I'm feeding it to the reg file, which is going to be the 1, 1 option on that reg file mux. Yep, looks good, 1, 1. And then I have I got these two store instructions. Well, the store instructions have nothing to do with the It has nothing to do with the reg file. It's actually reading something from the register file, so these are actually don't cares. Don't care. Okay, so I don't really care what those are. I don't have to put those in there. So these two here are using the ALU once again. The result from the ALU is being fed back around into the register file, and so I need to route it there using a 1-1. Okay, so I did most of these. I could do most of these problems from because I'm familiar with it, but there's obviously parts where I wasn't familiar with it. And I checked the spec. And sometimes I'm not sure what instructions are what, or what is routed where, and I need to pick those values up from the spec. And I used both kind of the written spec and also, more importantly, I used a lot of the architectural diagram. You should plan on using that too. This is not a class in memorizing a bunch of stuff. It's really a class in understanding the issues well enough to know where to look to find the answers that you're looking for. Okay, that is what I have.